This
doing that.
conference will now be recorded.
Okay, so I'm going to go into presentation mode. As you guys know, I can't see what's going on. So,
Right. And I'll let you know if anything comes through.
okay, great. And I guess, did Hal pop off or is he still on?
He's still on.
Okay,
Oh, there you know. Now he went. And I don't know exactly what this means, but he just went grayed out. So maybe
let's
he
see
didn't leave.
let's give him a minute.
Yeah.
But while he's doing that, I can quickly kind of go through the intro. So, it's been a while. We're here to talk about the Clear Roads project. I think it's 21-01, grip sensor technology and salt applications. And if folks recall, while we were able to get some data from this last winter, we weren't able to get a lot of data. And part of that was we identified two agencies, Iowa DOT and Colorado DOT, to partner with to get data from for this project. Iowa DOT was able to provide necessary RWIS and friction data to us, and that's what Hao is going to present on today. The reason we asked for the extension was the AVL systems in Colorado weren't sufficiently installed yet for last winter and the data was not available. So we currently have the project going through, I think, August of 2024 to allow for data collection for this winter. So I'll just go to the next slide. So we're going to provide just a quick project management update. Hal's going to go through his analysis of the Iowa data and provide some insights on what they've seen so far. And then if folks have any questions, we'll take those. So just as a reminder, because it has been a while, the goal of this project is to look at grip or friction as a viable data source in winter maintenance operations. So meteorological should be crossed out. That's a typo, and I apologize for not catching that. That should be winter maintenance. So basically what we've gone through and done is we wanted to look at what friction data is. We did the whole lit review, we did a survey, we even developed some case studies. And now we're to the point of, okay, well, how can we actually implement friction data in the context of making decisions about salt application rates? And that's really the core piece of this task is what does that friction data mean relative to all the other RWIS data and data elements that people are collecting in terms of as the plow goes by, what does that salt do to friction? So in terms of the project itself, we just submitted the quarterly progress report. The next one will be reporting out through December. And as I mentioned, there was a project extension that was approved and the new project end date is the end of August of 2024. And the goal was really to be able to capture data for this winter season so that we have more than one agency and one season of data to make this a more robust project. So I'll stop here and I'm gonna go out of sharing and see if Hao is back on.
Yeah,
and
he is.
I will
He's got
have him.
I'm sorry. I was talking over you. Yeah, he's got two sign-ins, but one looks like
Yeah,
it's
I'm here,
so
but
I'm gonna give it to
somehow
him.
the camera still doesn't work, but it's okay.
Yeah.
Not a big
Yeah.
deal.
So I will, if you want to take over sharing, I'll go off video.
Yeah, I just gave it to Hal's active sign-in.
Sure. Let me try to share my screen now. Sharing window. Are you seeing the full screen now?
Yep.
Yes.
Okay. So I will go ahead and give an overview of task 4, and Jingnan, she's a postdoc working on this project, and she will talk about more the algorithm details and also some preliminary analysis we have done.
So Hao, you can actually skip to slide 6.
I think it's here, right?
Yep, correct.
Okay. Yeah, so we are at task 4, basically developing algorithm and also decision metrics. So through the previous meeting, we mentioned that we kind of identified 2 data sources. Basically, the data has to including atmospheric variables and also pavement surface condition, especially friction, and also the slow plow track data, in this case, many salt application. And so two data sources are identified. First one is from Iowa DOT, which they do have the stationary outward station. We identified 3 locations at the beginning, but we use one of them for the analysis because 2 others actually showing some issues with the friction reading and also other things. We'll see some details later on. So in this case, we also have the AVL data from the plow tracks, but we do have to do manual matching. So basically, we're looking at what time the slow plow trucks passing the outward station, and then what's the salt application rate during that time window, and also what would be the friction reading from always. The friction reading from always is always continuously every 5 minutes, but we want to find out at what time the salt is applied and what will be the friction before and after that salt application. And most of the time, we do have 2 or 3 salt applications during one slow events. So this will give us a data, let's see, 2 hours after the salt application, what happened during the friction changing, and also after another salt application, what will be happening. So you will see some preliminary results from this data analysis. The second data source is from Colorado, which actually also Laura has been working with them in the past. The advantage of this one is they do have the tachymeter sensor installed on the plow trucks and also have the geotap spreader controller. So we'll be able to get the mobile friction data from tachymeter and also the salt application data from geotap controller. In this case, we don't need to manually matching that, but still we need to find out how many times this slow plow truck come back to the same location, because we do want to looking at the trend of the friction changing before and after salt application. That's a key actually for the algorithm development. In this case, we'll be able to find out if I'm applying this amount of salt at this climate condition on this surface, what will be the friction changing? And from there, we will be able to try to see, okay, what will be the trend or what will be the mechanism behind that, and then we can predict if I'm changing the salt application, what will be the friction changing, and then go back to providing suggestion for the salt application. So that's the 2 data sources we have here, and we have already obtained the Iowa data and also conducted the analysis. So basically, first we collect the data, as I just mentioned. And secondly, we process the data and integrate the data. This integration mainly is merging 2 data together because this is stationary outward station. So slow plow truck is kind of come to the location and also just go away. So we need to matching the same timing. And then we develop a machine learning algorithm. It's called the non-short-term memory method. So basically, this will be able to predicting the time-based changing of the variable, depending also many affecting variables. And also this method also will be able to considering the condition, the previous condition. So in that case, it's not only the affecting variables at the t affecting the output variable at the time t, but also we're considering the all variables t-1 condition. So in this case, you do have the time effect there. And after we develop the algorithm, we conduct a sensitivity analysis, checking, okay, is this method sensitive to salt usage or not? And then we, using this algorithm, try to providing the event-based decision making. So in this case, we are looking at one slow event, and then with the training, with the trained algorithm, we're changing the variable. For example, if we do have the salt application at the first salting or second salting changed, what will happen of the friction for this slow event? The second application case we are studying is the general salt application guideline. So our DOT has a table showing recommended salt application. Of course, that's based on both engineering practice and also other concerns, because too much salt also will cause impacts on the surface of the material degradation and also environmental impact. So they have that number actually not purely from the friction point of view, but we're looking at that table, we kind of assuming that table is a reference case, and then use the algorithm we developed to check if we do have the values in the table increase or decrease, what will be the changing from friction point of view. So I would say actually we kind of took a lot of time to look at the data and we look at literature, I don't think any study have really tried this way. So it's also new to us, and I hope we can get the comments from the panel and also really seeing if we really have the value from this method and can even conduct further study on that. So now I think, Jingna, you can go ahead to talk about the details about the data analysis. I can flip
Okay.
the slides for you. Yeah.
Yeah, thank you. Yes, I will take it over to introduce the detail of data processing and model development. So as we know, the RV stations are installed at fixed locations and provide point-based measurements to indicate the distance surrounding areas. So as suggested by the Iowa DOT RV's coordinator, 3 RV sites were selected as reliable data was provided at these sites. So including the Ankeny, Cedar Rapids, and the Iowa City sites. Since the change of road surface friction levels was not captured at the Cedar Rapids and Iowa City sites, so only the data from the Ankeny site was analyzed in this study. The pavement and atmospheric data collected by the Ankeny RV site during the winter seasons from 2021 to 2023 was processed in the study. So next, please. The atmospheric variables were derived from the atmospheric data set collected by the RV station, including the precipitation rate, wind speed, relative humidity, and air temperature. The surface temperature was derived from the pavement data set from the RV station. The data collected during the winter seasons in 2020 and in 2022 and 2023 was presented using the box plot separately, which will be also analyzed separately in the following section. Next, please. This is the precipitation rate and the surface temperature in the winter season from 2021 to 2022, and more than 30,000 observations were recorded during this period, so which was involved in the study. So next, please. This is the precipitation rate and the surface temperature in the winter season from 2022 to 2023, and the total number of observations was more than 30,000. Which were also analyzed in the following section. So next, please. Except for the infrastructure surface temperature, the road grade levels were also recorded in the pavement data set recorded by the RV station. The road grade levels could be categorized as high, medium, and low. The high level means the normal driving, and medium means some degradation of grip, which may be not noticeable except for braking or turning cases. And the low means the obvious and substantial traction loss. The change of grip levels could be observed by processing the data, and the grip levels of roadway near the RV site in a successive period was recorded, and the grip levels were impacted by the precipitation intensity and rate. Next, please. And the first plot shows the grip level during the first winter season, while the second one presents the change of grip levels with time from 2022 to 2023. It indicated that the grip levels became medium or low during the snowstorms. So next, please. To analyze the correlation, scatter matrix was plotted using the pavement and atmospheric variables. Surface temperature was found to increase with air temperature increased, and the surface temperature was also impacted by the relative humidity. But the relationship between other variables was not clear, So further analysis with an advanced approach was needed to investigate the potential relation between these variables. Next, please. Automatic vehicle location data was the other data set involved in the study. The rate and accumulation of solid and anti-icing and pre-wet materials applied by the plow trucks were recorded in the AVL system. In this study, the salt application rate was derived by adding up the application rates of solid and pre-wet materials. And this plot shows the range of salt application rate. Next, please. Since RVS and AVL data were from different data sets, so data processing was needed to interrogate the two data sets. This is a data processing flowchart. The snow information, such as start and the end of snowstorms, was extracted from the atmospheric data. Based on the snow information, the pavement dataset was filtered to derive the pavement observations during the snowstorms. The AVL data points collected around the RVS sites were extracted from the AVL system. Based on the time information, like the time interval, the pavement observations were matched with the AVL data to get the salt application rate for each observations. If there's no salt application for the observation, if there is no salt application rate for the observation, 0 will be defined for this observation. Therefore, we can guide the pavement observation with or without the change of grade flow levels in the whole winter season. Next, please. At the selected RVS site, Ankeny, the data are matched with the AVL data of plow trucks traveling within a 0.4 mile radius around the RVS site. The yellow pin shows the location of RVS station, and the orange points are the records of the plow truck locations traveling within a 0.4 mile radius around the RVS site. So this is how we can match the two data sets. Next, please. After data processing, we have get the interrogated data. This shows an example of a snowstorm. Grip levels change from high to medium or low after snow started, and improved after salt application. We can find multiple salt application implemented during a snowstorm. Next, please. This shows another example of the grip levels change with the application rate and the precipitation intensity. We know each snowstorm was recognized in the interrogated data set, so we can get the total number of total number of snowstorms in the whole season. Next, please. This is the salt application rate in the winter seasons in 2 years were analyzed. So totally 26 snow events, which last for hours or days, were found in the 2 winter seasons. And during each snowstorm, multiple salt applications were found at the RVS site. The salt applications after snowstorm were defined as variables Q1, Q2, and Q3. The box plot on the right side shows the first, second, and third salt application rate in the snowstorms. Next, please. Since the timing of salt application and the amount of application rate will affect the grip level of roadway, so we need to involve the influence of timing features in the model So the long short-term memory (LSTM) is considered in this was used in this study to develop the model. LSTM is one of the recurrent neural network, which is known as RNN. So RNN can store the patterns of recurrent input events in the form of activations. Or we can call this short-term memories using the feedback connections. So LSTM is a more advanced RNN architecture, which was designed to deal with circuits with better long-range dependency. The key elements of LSTM model include the cell states and the various gates. So this plot is a typical LSTM cell state with 3 logistic sigma gates and 1 10 layer, which is used in our study. Next, please. Okay. To develop the LSTM model, a total number of more than 80,000 data points were involved in the study, but mostly are observed in the light snow conditions. The inputs include the surface temperature, grape level, and atmospheric variables in the previous timing. And also salt application rate is another input in the LSTM model. The output is the grape level in the current timing. And this table shows the summary of the results, including the precision, recall, F-score, and accuracy. The precision is defined as a ratio of number of positive class prediction to the total number of positive to quantify the accuracy for the minority class, which are the medium and the low grape levels. And the recall is defined as a ratio of number of positive class prediction to the total number of true positives and false negatives in the dataset, which is used to quantify the coverage of the minority class, which also provides a measure of missed positive predictions. So F-score is a single score by combining and balancing precision and recall to properly summarize the model performance. This table indicates the acceptable precision, recall, F-score, and accuracy could be derived when we use the model to predict the grape level. So the derived prediction model could be considered as a reliable model to predict roadway surface condition. Next, please. The sensitivity analysis of salt application rate was conducted. The real salt application rate during 2022 to 2023 were used as the baseline case. And this shows the range of salt application rate and various surface temperatures in the baseline case. In general, the salt application rate increased with the surface temperature decrease. But we know this is the box plot of salt application rate, but we know this didn't follow the current guideline. So next, please. The sensitivity analysis was conducted by increasing or decreasing the rate by 50 to 100 pounds per lean mile as compared to the baseline. So the effect of salt application rate on grape level was investigated, and the results was plotted using the first bar plot. And we can find a linear relation between the change of salt application rate and the grape level. Next, please. So now the proposed LSTM model can be used in 2 ways. First, the model can be used as an event-based decision-making tool. This is an example of grip level prediction after salt application rate applied on the surface and during a snowstorm. And we can see the increase of salt application rate improves the road grip levels. Next, please. This is another example of grip level prediction after salt application. And the decrease of application rate leads to a degradation of grip level during a snowstorm. This can be observed in this case. Next, please. This shows another example, and after seeing these three examples, we know the influence of salt application rate on the road grip levels can be analyzed case by case using the model as a decision-making tool. So, which means this is the first use of the proposed model. So, next, please. The other application of the model is to refine or adjust the current guideline. So in this case, another baseline was created by using the salt application rate in Iowa DOT guideline, which is marked in the red rectangular here. The salt application rate in the guideline is determined by the surface temperature and the precipitation intensity, or we can call it the snow intensity. Next, please. So similar to the previous case study, the salt application rate was increased or decreased by 50 to 100 pounds per linear mile, and the increase of salt application rate improves the road grip levels, and the influence can be quantified using the model. But we still need to consider the balance of road grip level, cost, and the environmental impacts in the future work when we want to use this model to determine or adjust the guideline. So this is the second use of the model.
And let me take over from here. So basically, we tried the data set from Iowa, which we assuming, for example, the trend friction changing from Iowa data is right, because that's the basis of machine learning. We have to using the training data set. So in fact, we are using the 2022 data as a training, and then we are using the 2023 data as verification. So if you go to previous slide, there's one slide here actually showing these summary results. Basically, you can see the precision, recall, or F1 score. You can treat them as indicating of the accuracy. So 1 is the best. Less than 0.5 basically is showing not good. And then corresponding to high, medium, low is the model be able to correctly predict the friction condition as medium or low. So you can see the high is 1 because we have so many points which are high friction, because the slow events are not many. Even during this 3 or 4 months period, 26 slow events were there. And for the slow events, only last like days, 1 day or 2 days. So most of data points along the winter period is high friction. So that's why this high friction was predicting very well, because basically it doesn't change it too much. And the medium and low actually are showing, okay, because of slow and basically friction changing, and also after salt is also changing the condition. So you can see generally we're talking about model accuracy around 0.7 to 0.9, really depending which aspect. So that means the model is acceptable, although it's not the best. Again, this is really depending on the training data set. So after that, we looking at the event-based decision making. So that's really looking at if in future we have the ability to tell the slow plow truck driver, okay, you should use salt application at this rate because we have this kind of surface condition temperature. And currently, I think their work has been done at some states are trying to do that, but they are more like using the table way or guideline way. So basically, give you a table showing, okay, if you do have this temperature, if you do have this um, condition, you probably use this rate. But this algorithm actually give a little bit more dynamic way or real-time way. So if I do have the condition that this atmospheric condition, the surface condition from always feeding to the model, be able to predicting what will happen using different slot application rate. So that's why we call it event-based decision making. The second one is really looking at the guideline used by our DOT as a general comparison case. And then some limitations have to mention because as I mentioned, this is a first try of using this advanced method for decision making. In this case, we kind of using AVL data to matching the RV sites. So we do the manual matching. So and also really depending if this AVL truck is traveling in the lane which actually having the always sensor or kind of in the adjacent lane. We match the direction, but we're not able to matching the lane effect. And also the slow plow effect was not included because the current AVL data from Iowa doesn't have this plow operation. This can be addressed in the second data set we'll mention shortly. So this will affecting the model accuracy, but at least the results now indicating the model is acceptable to predicting the condition based on the atmospheric condition, previous surface condition, and also the salt application. So next step is we will looking at a second data set, which will get a sample from GeoTap for AVL, which including both plowing and also salt, and also get the mobile friction data from Tacona and the atmospheric data from always steel. Basically, that's also has to be coming from always because the climate variable was not measured actually with a mobile sensor. And then we'll see if the new data set is able to improve the model because that we do have the plow data, but also depending how often this plow truck is going back to the same location. As I mentioned before, we're really looking at the temporal changing of the friction as the climate condition changing and the salt application. So in that case, the more often the slow truck coming back to the same location, the better for the model point of view, because in that case, we'll be able to predict how this friction is changing before salt and after salt, and then after second salt application. So that's something we are working with GeoTap and Tacona now. And expected outcome, so we will provide two also decision-making methods. One is more like event-based. In this case, the algorithm can be provided, and then once the data is inputted to the algorithm will tell you for these slow events what will be the friction after certain application rates. And we're also looking at if we are adjusting the current values in the application table or guideline which state DOT have, what will be the expected changing in terms of the total service condition over the whole winter. So that's what we have for now, but we're open to any questions, comments. Yeah.
So
And
I
I think we are,
received.
yeah,
Oh, I'm
we're done with
sorry. I just saying I received a chat message, and you probably saw it too, from Matthew Hines from Texas DOT. He seemed pretty satisfied, but had to jump off. So
I think one interesting thing that for me, reading, what came out of this analysis is that so far, even with this kind of just one season, two kind of isolated locations, what the algorithm is showing is that more salt equals better friction. And Iowa DOT has very clear and tight guidelines for their application rates. So one thing that Hao and I kind of were messaging before this call was that piece that Jingnan mentioned is, I think we're all inherently aware that more salt will likely give us better friction, but we need to really hone in on, what application rates are going to fall within your guidelines, and then let's be cognizant of cost and impacts when we say this, because ultimately, the algorithm could end up saying, everyone should put down 500 to 1,000 pounds per lane mile, and then you'll get great friction. But that's not going to be helpful in the long run necessarily.
That's
Yeah,
good,
I agree
Laura.
with Laura. Yeah, but and one challenge is also the benefit side, right? So because now we do see the benefit is, for example, we do have short time period of the friction with no friction. We have more time, for example, with high friction or this high or medium friction come back quicker. But how to really quantify the benefits of this, right? Because um, this related to accidents, but doesn't mean if it's medium or no friction, accidents will happen for sure. So that's also challenging there. The real benefits caused by high grip is kind of really difficult to quantify. Yeah, but I think that's definitely deserve a further discussion. I mean, although it's not in the scope of this project, but interesting to discuss that. Yeah.
So, what do you think is the estimated timeline for getting the data set from Colorado? Are we waiting for the next winter season? Is that what?
Yeah, so we've been working with Geotab and CDOT for a while now. There's been a little bit of a hang up. There's like two storms from February of last year where a few trucks have some data. So we've been trying to get a practice data set from them, and they were supposed to deliver it on Wednesday and they hadn't yet. So we have all the permissions from CDOT. We have data ready to be grabbed from Taconic. We're just waiting on this Geotab data set. So essentially we'll have practice data from February of 2023. And then the goal would be, because Colorado did a full rollout install of AVL on almost all their trucks, we'll have AVL data for all the plows that have Taconic sensors on them, which I think should be 5 to 7 for this next winter that we'll collect data on.
Okay, yeah, that sounds good.
And then the great thing about Colorado, I think a lot of folks know, is that they have a very robust stationary RWIS sensor network. And so with that RWIS data, we'll have the mobile data, but then we'll also have the stationary friction data. So it's a little bit more of a deeper analysis, whereas Iowa just has the stationary friction sensors.
Okay. Yeah, so I know Tom is on here. Tom, I don't want to forget you if there's any questions or comments that you have. I want to make sure that you have a chance.
No, I don't have any at this point. Sorry. I couldn't
Okay.
find the mute button.
All
Sorry.
right. Thanks, Tom. Okay, well, I think this was a good update. I appreciate that. Obviously, so we're relying on two states' data. We've got one. We're working on the second. This was the reason for the amendment to extend this project. This task goes on through May of next year. So we've got plenty of time to work on that. And then the final recommendations, report, webinar, wrap up over the summer of next year. So I think we're in pretty good shape. So I just want to check back, Laura, as we said, we're recording this. I will post it and notify the subcommittee that they can go review it. But is there anything in particular that you need at this time from the subcommittee based on their viewing of the recording?
No, this was really just an opportunity to check in with folks, let them know that we are doing work. And hopefully, with basically in the next couple months, the goal is to have some of the preliminary analysis of the Colorado done so that when we do get the bigger data set, it's just more of a plug and play. So I would suggest once we have the Colorado data processed, we do maybe another check-in meeting. And then in the spring, once the full data set for this upcoming winter's processed, we have that task meeting.
Okay, so you're suggesting that we have another meeting after the full data set's been processed?
Maybe even before then, after the
Oh,
initial
the
Colorado.
initial, okay,
Yeah,
okay.
just to
So
check
later
in and let
fall,
folks
early
know
winter.
kind of, right,
Okay,
what the mobile data is looking like in terms of this analysis.
okay. No, that makes sense.
And
Okay,
we'll be in touch basically once we have the data and the analysis is happening. So again, we were
yeah,
supposed to have it Wednesday, so hopefully we'll have it by tomorrow.
okay. Gotcha. All right. Good. Well, I don't have anything else. This was really informational and good information, and I appreciate it and understanding kind of where we are right now. I think that it would have been great if we could have had everybody, but considering the kind of meeting this was, I think this worked to proceed as we did. And like I said, I'll get that recording posted, and we'll just keep the group informed as we move forward. And I just again appreciate everybody from the research team for your time today, and wish everybody a good weekend. Hopefully it's better than it is here. It's all rainy and chilly.
Thanks for coordinating this, Greg.
Okay. You guys take care.
All right, bye everyone.
Thanks, Greg.
Bye-bye.
Thanks, Greg. Yeah, thanks a lot. Gina, thanks. Yep.